So starting with the cross section area of sewer, that is the design parameters. If you just revise, so sewer design, it is including the fixing the cross section area. So this cross section means nothing but it is the area and the slope of the sewer. So these two things we have to calculate. Now we know that most of the sewers are generally designed as, it is generally designed as circular cross sections. Okay, now in these circular cross sections, some geometrics are the diameter of the pipe, and we know that we generally do not allow the sewage, which is flowing inside this, or we can say that we do not allow the full capacity flow of the sewage through this pipe. So sewage, there is always some empty space that is provided. You can see this is an empty space here. So this empty space is provided to accommodate the unexpected maximum flows. So if you just try to take the practical example, let's say before rainy season, the sewage level is up to this. Okay, so average level of sewage is this, and during the rainfall, what will happen? So along with this sewage, rainwater will also come into this sewage due to the rainfall. So if you remember the sewerage system, in that the first sewerage system was combined sewage or combined system. So in this combined system, the sewage was designed for dry weather flow. This dry weather flow means it is the direct sewage, okay, and wet weather flow. So what is the meaning of the wet weather flow? Wet weather flow means nothing but the rainfall only. So if this sewage is only flowing in the full capacity and then there is a rainfall also, excess rainfall, then what will happen? The capacity will be breached and there will be overflow of this sewage. So to take that into consideration, we generally don't allow the sewage to run into a full condition, that is we keep it at half or partially full condition. Now, so starting with the basic introduction of this topic, so just write it down. Cross section area of sewer. Cross section area of sewer. So we generally consider the circular cross sections. So that only will write circular geometric cross sections are preferred to other geometrics. Okay. Sewers always flow with partial flow condition. So empty space is provided in sewer to accommodate unexpected incidental flows. Okay, now so we'll be seeing the four major cases, and in all the four major cases the design considerations will be taken. So the four major cases, I will just summarize it here, what we are going to see. So in the first case, we are going to see a sewer which is running full. Okay, a sewer which is running full. So what is the meaning of running full? That means the sewage, or there is no empty space which is present in this. So it is running completely full. Now in the second case, we'll take the sewage or the sewers. They are running. The sewers are running half. Okay, so if we take the total capacity, so it will be 50% of it is utilized. In the third case is we don't know the exact level, so we'll represent it with the other geometrics like theta. So let's say this is the mid level and the sewage is present up to certain level. Okay, so for this what we will do, we'll take the center of circle, and we will calculate the radius here. So whatever the radius is there r, and we'll give some other geometric parameters here. So like this angle is theta. Now with the help of this we'll try to calculate the area of cross section and also the velocity and the discharge. Okay, now the last condition is, so it is running somewhere between, or we can say it is running more than half. So this is the 50% line, so it is running up to here. The sewage is running up to this point. So in this case also same thing we'll do. We'll draw the diameter which is at 50%, take the center of circle and draw these lines here up to this point. So this is the radius and the angle which is subtended here, this is alpha. Now based on this we'll try to calculate the other parameters. So this is less than half and this is more than half. So let's start with the first case. Case number 1, sewers running full. Sewers running full. So now from this topic you just see the diagram and the formulas we will derive it. You just have to remember those formulas. Okay, in this case, so it is a completely numerical concept. So this is the circular cross section and the sewer is running full. This is the sewage and it is completely filled. Okay, so in this case now the first formula is weighted area. Okay, weighted area, that is what is the amount of area that is in contact with the sewage. So that area is called as weighted area. So this diameter is capital D. This diameter is capital D, that is overall diameter, and the depth up to which the sewage is present, that is small d. So in this case the weighted area A is equal to pi d square by 4. Then the next is weighted perimeter. So same, the perimeter of the sewers which is in contact. So how to calculate this is the total perimeter which is contact. So total perimeter is 2 pi r, or we can write it as pi into d. So this is A and this is P. So the next definition is the definition of hydraulic radius. So hydraulic radius. So hydraulic radius R, this is calculated as a weighted area by weighted perimeter. So if you do this calculation, pi d square by 4 by pi d, you will get here the answer as d by 4. Okay, so this value is important. Now we know the two formulas here. So what are the two formulas that we know? So V is equal to Manning's formula 1 by n r to the power 2 by 3 s to the power 1 by 2. So here this n is constant value, r is this d by 4 we have calculated to the power 2 by 3 and s to the power 1 by 2. And similarly q is equal to area into velocity. So area we have calculated pi d square by 4. So this is pi d square by 4 area multiplied by velocity. In this first equation we have calculated. So 1 by n d by 4 to the power 2 by 3 s to the power 1 by 2. So now solving these equations, we can get all the values, or we can say solve these two equations. When we will see the numerical, it will get more clear. But see, these are the two formulas, and the quantities that we are using in these formulas, we are deriving it like this. Okay, in the problem the case will be given that the sewers are running full, the sewers are running half, the sewers are running more than half. So you have to see which case it is and then apply these formulas. Okay, so next case, sewers are running half full, sewers running half full. Okay, I guess the circles are getting more good now. Okay, so this is the level of water, the level of sewage which is present in the sewer. Now what is the total diameter? The total diameter is capital D. But what is the depth up to which the water is present? So small d. So it is present at a depth of d by 2. So this is the d. Now same formulas, weighted area that is A is equal to, so half of the area is in contact, so it will be half of the previous formula, that is pi d square by 4 divided by 2. So it is pi d square by 8. Now weighted perimeter P is equal to, so half of the perimeter will be there, total perimeter pi d, so in this case it is pi d by 2. Now hydraulic radius R, this is equal to weighted area by weighted perimeter. If we do this, then it should be the same value. Okay, because in both the cases we have divided with the 2 only, so we'll get the same value here. So you can just mark this one point, that hydraulic radius for the both hydraulic radius for both sewers running full and sewers running half is same. So write down the note, hydraulic radius, or just write down, I will write it down R only, you write it completely. R for case 1 and 2 is same. So this can be asked as a MCQ. Okay, now so with this, now same, you can apply the formulas for V and Q and then get the values. So even we can write it down. For this case I will write down, for the remaining cases you can just write the formulas. So V is equal to 1 by n r to the power 2 by 3 s to the power 1 by 2. So 1 by n, what is the value of r? D by 4 to the power 2 by 3 and s to the power 1 by 2. So Q value is area into velocity. Area in this case is pi d square by 8 into velocity is 1 by n d by 4 to the power 2 by 3 s to the power 1 by 2. Now in this case also you just write down one important point, or you can just see it here. See, velocity in this case 1 and velocity in case 2, the both are same. Okay, so velocity in case 1 and 2 is same. However, discharge, that is Q, in case 1 and case 2, are they same or different? So you can see velocity is same, but if you look at this area, weighted area, so it is pi d square by 4 in the first case, in second case it is pi d square by 8. So it is not same, So these 3 points are very important. Okay, so which things are same and which things are different in the first two cases. Now, so we'll go to the third case. So Sievers running less than half. Sievers running less than half. So this is the 50% level, excuse me, and this is the center of the circular siever. So if we just take the level here and join this, and let's say we have taken this angle as theta, we have calculated this angle as theta, and r is the radius. So in such case, the weighted area A is calculated as weighted area. Okay, so this is a purely geometric formulas. You just write it down. R square, it is r square into theta minus sine 2 theta by 2, and weighted perimeter P is equal to 2r theta. Okay, so then you can calculate the r value, that is hydraulic radius. Hydraulic radius formula is A divided by P. So you just substitute this and get the value. Now let's see quickly the last case, that is case number 4. Sievers running more than half. Sievers running more than half. So this is the 50% level. Now more than half, so let's say the sievage is present up to this level. Now first we'll mark these two levels. Up to this point it is present. Okay, this is the value of radius r, and this value will give the name now as alpha. Now pay attention here, this value is alpha. Okay, but we want this angle because this is our theta. So how to calculate this? So this is calculated as theta is equal to 180 minus alpha, or if you just write it down more properly, let's say this half of the angle is, this is alpha. So if this is alpha, then this remaining also is alpha, and this total angle is 2 alpha. So if this is alpha, this is also alpha, and this is 2 alpha. So if it is symmetrical, now how to calculate the remaining angle, that is this angle? How we are supposed to calculate this? So this is, let's give this name as 2 theta. So total is 360. So 360, or we can say 2 theta is equal to 360 minus 2 alpha. So theta is equal to 180 minus alpha. So same thing, you write it here. So first calculate alpha, then calculate theta as 180 minus alpha, and then same formula you use, that is weighted area A is equal to r square into theta minus sine 2 theta by 2, and P is equal to 2r theta. Then r is equal to hydraulic radius A divided by P. So with this now you can calculate the discharge and velocity, weighted area, weighted perimeter So all the design parameters are completed in the 4 cases. So by heart these formulas for all the cases, and the most important formulas are only for the first 2 cases. If you are preparing for the GATE exam, then it is important to learn the case 3 and case 4 also, because that can be asked in that level of exams. However, for the JEE level, it is sufficient for us to learn up to the case 1 and case 2.